So we're going to look at not two different ways, but one way to approximate a solution given a difficult function or a difficult kind of like differential equation. Okay? And so we're going to use a tangent line approximation. All right, so looking at a problem like this, all right, we're asked to approximate the value of f of 1.02 using the tangent line to f equal to, it should be really f of x, I guess. F of x equal to 5 minus 3e to the 2x minus 2 at x equals 1. Okay, so let's kind of stop and just kind of appreciate what we're being asked to do here. So if I were to give you this function right now without a calculator and ask you to evaluate this function at 1.02, you know, we'd have a problem there, right? Because, like, okay, we could do 1.02 times 2, it's 2.04. We could subtract 2, and it'd be 0.04. But then to evaluate e to the 0.04 without a calculator, you'd be like, not really sure what the value is there. And then to multiply by 3 and do 5 minus that, you, again, would still be really stuck, okay? So this function is too complex for us to evaluate this right now without a calculator. However, if we come up with the tangent line to this graph at x equals 1, okay? Now, why do we choose x equals 1 here for our point of tangency? Because it's close to what? 1.02. We're trying to approximate 1.02, so we'll find the tangent line at x equals 1. Because if you look up here, the tangent line, I know this is not obviously the same graph, but the tangent line of a function is very close to the actual function near that point of tangency, right? So we'll say like the point of tangency maybe is like right here. The curve is very close to that tangent line near that point of tangency. So we're gonna utilize that characteristic there. We're going to take the tangent line to this function at x equals 1 and then use that to approximate 1.02. All right? So in order to use a tangent line to approximate 1.02, we need to come up with the tangent line. How do you find the equation of a tangent line?
Derivative.
Take the derivative of the function. So let's go ahead and take the derivative here. So f prime of x then is going to equal, the derivative of 5 is 0. The derivative of negative 3e to the 2x minus 2 is negative 3e to the 2x minus 2, right? Times 2, right. Don't forget to multiply by the derivative of what's inside. So times the derivative of 2x minus 2, which is 2. So we simplify this sum. It simplifies to be negative 6e to the 2x minus 2, right? Okay, we took the derivative. So is this the equation of my tangent line? What is this? It's what we can use to find the slope, right? It's the slope at any x-coordinate. Specifically for us, we want to find the tangent line at what point? Right, x equals 1. Remember, our goal is to eventually estimate 1.02, but we're writing the equation of the tangent line to f at x equals 1. So we got to find f prime of 1. So it's negative 6e to the 2 minus 2. Okay, e to the 0 is 1, so this ends up being just negative 6. Well, that's really nice. Okay, so this negative 6 is what? The slope of the line tangent to f at x equals 1. Is that enough to write the equation of a line then? What else do we need to write the equation of a line? A point. We have an x coordinate. How can I find the matching y coordinate for this point? Plug it in. So I'm going to do f of 1 now. It's 5 minus 3e to the, 2 minus 2. So e to the 0 is 1. So 5 minus 3 is just 2. And so I have the point 1, 2, and the slope of negative 6. And so to write the equation of the line, it's, what's point slope form again?
Y minus y1.
Yeah, y minus 2 equals m, the negative 6, times x minus x1. So there's the equation of our tangent line. Okay? So there's the equation of our tangent line, and now what are we going to do? plug in 1.02, exactly right. We want to approximate the value. Remember, value means we're solving for a y-coordinate of f of 1.02. So we're going to plug that 1.02 in for x. So y minus 2 equals negative 6 times 1.02 minus 1. And so y equals, I'm going to add the 2 over, so we get negative 6 times 0.02 plus 2. Okay, do y'all remember how to do the decimal arithmetic here? Okay, so you multiply it like normal numbers, so negative 6 times 2. So think of it as like negative 6 times 2. It's negative 12, but then you have 2 decimal places, you got to move it over, so it'll be negative 0.12. Okay, plus 2. Right. It's just like you would, so negative 6 times 2, negative 12. And then, but it's 2 decimal places removed, so then you're going to just move the decimal place back over 2 decimal places. So again, basically, I moved it right 2 decimal places to do 2 times negative 6. I moved it back over 2 for that. That's the idea. Okay? And so that gives us then, what, 1.88? And there it is, approximately. Now, that's approximate.
Why?
Now let's use our calculators to see how close we got.
Why is it approximate? Because we use 1 to find the equation that we use.
Remember, this is the original function, right? I want to approximate the value of this function at 1.02. I use the tangent line at x equals 1, which is a nearby point. Why did I pick 1? Because 1's a nice whole number, so it's easy for us to mental math, you know, the slope and the point. So let's actually type it in our calculators and see what happens here. So 5 minus 3e to the 2 times, what should I type in for x here? 1.02. Yeah, we want to type in the 1.02 minus 2, close the parentheses there.
Oh my goodness.
1.877, we got 1.888. Well, that's pretty good. The 7 would round up to 1.88, so that's pretty darn good. Pretty close. Okay? So why don't you all go ahead and try number 6 there then. Okay, give number 6 a shot. Okay, again, no calculator. No calculator, please. Try it sans calculador. Or sin calculador.
Are these typically for response questions?
It could be. Could be.
Buddy. Well, because square root is not power negative 1. Power 1 now. Did Mr. Drum leave a sub-report?
He did.
We said we were awesome.
He said you guys did well. So they You guys wish that you had taken the algebra test instead of his algebra students, because apparently his algebra students did not do very well on the test.
No, I'm not happy. He was livid.
It was like, how long does it take for this? And it was in feet.
I know. Yeah. Yeah.
I was like-
And I was like, of course, Mr. Drum. You said how long? Feet is the length. Come on. What's the problem? Nope. That's why Algebra 1 is like my least favorite. Algebra 1 year long is my least favorite class to teach. Yeah, well, they made Algebra 1 Common Core a year-long class now because it's actually really tight to fit in all of the topics into an 18-week class, like a semester class. So they have it semester 1 and 2, 2 semesters. Common Core Algebra 1. You would have taken that 8th grade? 7th grade, maybe?
Yeah, 7th grade.
So we
We
got
got
to
Common
7th
Core
grade.
then.
Yeah, you missed it. You're lucky. Yeah. There's a lot of Algebra 2 stuff in there now. They do like quadratics and factoring and things. Say again? Yeah. And you're talking like the lowest level freshmen have to take that Algebra 1 Common Core.
What are the highest?
High school freshmen will be doing geometry when they come in.
So
You can't take
basically,
geometry in middle school anymore.
they're a year behind.
Essentially, yeah.
Don't they have to like double up every year to get to calculus?
No, they can still get to calculus. They will have to level up once to get to it before their senior year. Yes, if they wait, it would be geometry freshman, algebra 2 sophomore, junior would be pre-cal, and then senior year. But normally, what you can do is double up algebra 2 and pre-cal pretty easily your sophomore year, and then pre-calculus your junior year. But then, yeah, well. Sine of pi is 0.
Yeah.
Cosine of pi is -1. Okay. So 4 to the -1 at 1.5
Wouldn't the
times.
4 go away?
Or deposit 1/2. So it's 2. So it's -5 halves. -5 fourths.
Well, no, wouldn't it be 20 minus 20? Oh, no, it was 1/2 and 2. Wait. So you'd have 1/4.
1/4 to the 1/2.
Yeah, but multiply by 1/2 will it be the 1/4?
4 to the 1/2 is 1/2.
Yes, multiply by 1/4.
Times 1/2 is 1/4.
Yep.
Times -5 is -5 fourths.
Time!
It's multiply.
I'm the derivative of my
Big
goof.
You silly goof.
I goofed. I was like, no wonder my answer is so ugly.
Sine of pi is 0, so it's the square root of 4 plus 0, which is just then 2. So we get y minus 2 equals -5 fourths x minus pi. So we plug in 3. And now obviously this one, we can't do a whole lot of simplification here because, oh wait, no. Yeah, that was right, never mind, shoot.
Hey, you just didn't add this 2 over.
So, obviously for this one we can't evaluate it too much because 3 minus pi, well that's irrational still, so it doesn't really help us there, but there's your kind of unsimplified answer. So we type that into our calculators, okay, just kind of see it, -5 fourths times 3 minus pi plus 2, so you get about that. Alright, and then if I do the square root of 4 plus 5 sine of 3, again we're approximating the value of f of 3, so we're going to plug 3 in there. We get that. So again, we're pretty close. We're off by, what, 0.11?
About, yeah.
0.11, 0.12.
Can you move the calculator for a second?
Okay.
How did you get negative?
Are you okay up to this point?
Yes.
4 plus 0, 4. 4 to the negative 1/2 is 1 over 4 to the 1/2.
If it was steady, I would mess myself up.
Just do 1/2.
If it wasn't
I
steady.
just look at the square root of 4. I was like, what is it?
Okay.
A squared.
Questions? Sorry. Yep. You're okay? Seriously?
I think so. Wait, why the 3 minus 5?
Because, so this is the equation of your tangent line. But again, why do we write the equation of the tangent line? Yeah, right. Watch this question, guy. Why did you write the equation of the tangent line? What was the point? The point of the tangent line was to approximate the value of f of 3 using the tangent line.
Oh.
So if I want to approximate plugging 3 into this, I'm going to plug 3 into my line. So that's why. Okay, that's right. Okie dokie. So we're going to take a look then now at...
Oh, more notes?
Yeah. Because this was just finishing up what I wanted to get through yesterday. Yeah, now we're back on track.
Are these notebook notes now?
I think so. Let me just check to make sure, because I want to make sure that I don't need to print something out for you guys, which I should have done already, but obviously I didn't, so...
She's holding favor here. Holding.
Okay, yeah. So, here we go. Piece of paper out. Piece of paper out, please. Piece of paper.
Oh, gosh. There is a favor. That eye roll.
Okay. So, and I don't know how important this is for you to write down, so you don't need to write this down necessarily if you don't feel like it's important. Okay. We know how to solve differential equations of the form y prime equals f of x. Okay, so what I mean by that is, like, if we have y prime over here, which is like dy dx, is equal to something in terms of x, right? Only if there's a bunch of x's over here, we can solve that, no problem. We just integrate both sides, right? That's what we would do. We would just integrate both sides there, okay? Now we will learn how to solve some general types of differential equations, but there will still be ones we can't solve. I'm going to abbreviate there, of diff EQ, by rewriting the equation so that each variable is on different sides of the equation.
Yeah, so we're doing in physics.
Okay. In other words, this is called separation of variables, right? Just like in real life, when you want to separate people to destroy them. To solve them.
To solve them. Okay, Mr. Dan.
Okay. Then you want to do that in math too. Isolate the weird thing, right? Just like in real life. Isolate the weird thing, and then you can solve the equation now. Okay? We train you to do that. All right.
Selection. Social Darwinism.
So, right. So solve the different. So here's an example. So here you want to start writing now, I'd say. If you didn't before, that's okay. Solve the differential equation I said that, right. It's up to you. Notes are always for you guys. I mean, like, is it important? Is it not important? I don't think that, I mean, that's just kind of introductory. Okay, now your hand's tired. I'm sorry. So, this is different than problems we have done in the past, right? What's different about this now? What's unique, or what stands out to you? There's x's and y's in this differential equation, okay? We have run into derivatives that look like this, right? When we did implicit differentiation, sometimes we had x's and y's kind of mixed together there, where we had, you know, dy dx equals that, all right? So we're going to now solve this. We're going to work backwards, okay? We're going to derive this, anti-differentiate this. So we're going to get to that. So what we're going to do is, so to solve, separate the variables. Okay. So I'm going to rewrite y prime instead as dy dx equals 2x over y.
I see what you're getting at.
All right, and we want to get the x's and dx's to one side, and the y's and dy's to the other side. Now, I'm going to make a recommendation here. As soon as you get your dy over dx like this, multiply the dx over. All right. So, if I multiply both sides by dx here, I get dy equals 2x over y dx. Now, some of you guys will look at me and say, Mr. Meyer, why don't you also just multiply both sides by y? You could do that as well, simultaneously, you're right? I'm just trying to show you very, careful step-by-steps here, okay? But again, my recommendation to everybody, you don't have to do this, but it's a good idea, is as soon as you write it as dy dx, multiply both sides by dx. So that way, essentially, you're always going to end up needing to get your y and dy's to the left, and your x's and dx's to the right. Okay, y's and dy's to the left, x's and dx's to the right. And that's because we're used to seeing that way, so I think it'll just help you to get things right. Now, have we entirely separated our variables here yet? No, because we still have a y mixed in here with our x's. So what do we have to do to this y? Multiply both sides by y. So that y and the y cancel there. We're still left with y dy equals 2x dx. Have we separated our variables now?
Yes.
Yes. Y's and dy's are on one side, x's and dx's on the other side. They're separate but equal. Huh. Say again? We could have just cross-multiplied, yes. But later, Maya, we're going to see more like complicated ones, and so that's why I want to get us, again, I want to make sure we have the very, basic fundamental stuff down, and so that way when we get to the more difficult stuff, it'll be more familiar. So yes, absolutely, though, you could have just cross-multiplied. Okay, so now we integrate, right? Now they're separate but equal, we integrate them. It's just really weird that it's like so...
Yeah. Okay.
Really weird. I feel like I'm teaching you social studies without even trying here. Okay, so anyway.
Separate but equal.
So but now we're going to integrate. So, all right, what's the integral of y with respect to y? 1/2 y squared plus c. Okay. What's the integral of 2x dx? X squared plus c. Okay. So, because we integrated here on both sides, we end up with a c on both sides. But the good news is, we don't have to I guess we can combine these c's together, okay? And so, to do that, you might say to yourself, all right, this is like any other equation. I'm just going to subtract c from here and subtract c from here, and the c's are just going to cancel. And the answer is, yes, normally, but because these are constant integration, we want to just kind of absorb one into the other, and so we can just write it this way, basically. Okay, we can just leave the one c. The other c just kind of goes over and absorbs. Okay, but I still have to write these plus c's here because I did integrate, so I need to show that I am getting a constant integration there.
Can we solve for a variable now?
And so, yes, typically to solve the differential equation, you want to isolate the y. Okay, because normally when we write the equation, we get the y by itself here. So, let's get the y by itself. So what would that entail here?
Divide by 1/2.
Or multiply both sides by 2. Notice I don't write 2c, I just write c, because what happened to that 2? It absorbs into the c. You can write 2c, that's fine, but you don't have
Is that
to.
the same for square roots?
So we'll hold off on that. So now what should I do to both sides? Square root. Right, and don't forget plus or minus. So it should be y equals plus or minus the square root of 2x squared plus c.
So
Okay.
it does stay under the square root of c.
Right. Well, yes. That's as far as we can go, right? Can you break a square root up over addition?
No.
No, you cannot. A product, yes. So if this was 2x squared times c, then you could do the square root of 2x squared times square root of c. But because it's addition, you can't break it up like that. So that's your final answer right there. That's the solution to that differential equation. So this function, right, is its derivative is equal to that original differential equation there. Okay. So if we were to graph the slope field for this, right, so imagine all the little slopes, and if we picked a particular point, like the point 1, 1, for example, and then we use the slope field to kind of guide ourselves, we would get something that looks like this. Okay, we would get something that looks like that. In fact, we didn't do that one, did we? No, we didn't. Sorry, hang on, I just want to see. We did not. Okay. So I kind of want to show that to you here. Let's see if I can get you one. X squared over 2y squared. Okay. Okay, we'll hold off on that. So I'll show you that in a later time. But anyway, we'll take a look at that. All right, let's look at another example here. Let's try another one. So we'll solve the differential equation.
Do we always isolate y? Will we ever have a case where we isolate x?
Generally, we're going to isolate y. I can't think of any time where I've ever seen them ask you to solve for x here. Now, sometimes they'll change the variables up on you and make it like w's and, oh shoot, I just wrote a w because I thought it. W's and T's or something like that, and then you'll kind of like, I'm not sure which one's X and which one's Y. Well, you just have to use W's and T's. Okay. Okay. So actually, why don't you guys go ahead and try this one? I think you can do it. Give it a shot.
Get it done.
We're going to change y prime to dy dx to help you out. It depends. Like this is, like I said, this is very close to what a free response question would be like, but like simply doing something like this would be roughly 6 out of the 9 points if you do it correctly. Not a mistake. They're a little bit more complicated than these, but not that much more.
I'm saying, like, you think the breakdown points for like dy dx and showing the integral and then one and then the solution, and then where's the other one?
So it would be like separation. So it'd be dy dx equals that, and then yeah, it'd be like, I think it'd be separating variables. So that's 1 point. Then I think you get a point for a correct integration on both sides. That's 2 points. So that's 3 points. Then you get a point for plus c, like knowing what plus c. Then you only get a point for plugging in the points, like to get a particular solution. So you can say you have a particular solution, you have several solutions at that point. I think you get the 6 point then for then correctly writing the final equation and solving for y. So that's where the 6 point comes from. So here we're missing 1 because you're not a particular solution C, but you should still isolate for y.
So is the separation variables, like, if you had, like, this is my separation, and I just set it with an integral sign.
Yep, that's fine.
That would be 1 point.
Yep, and then the actual integration here with plus c, that's another like possibly 2, definitely 1. with the plus C, it's either 2 or 3. Sometimes you get one for each side and the plus C, sometimes you get just one overall and then the plus C. But yeah, it's pretty, those are like,
It's very
good.
forgiving question.
well, it's like a place where you can like really get a lot of points there easily. Not easily, but following just like normal kind of process. Because again, with most of your response questions, you have like an A, B, C, sometimes a D kind of section. With these, it's only like an A and a B, and that's it. Because this is worth so many points. All right. Let's see how we did here.
Oh my god.
Let's go to, someone who's in my class. There we go. Chanda! Okay, Chanda. So we had to change this to dy dx equals x squared over 2y squared. Then what? Okay, and also I'm assuming you multiply the 2y squared over 2? Okay. Okay, then what? Integrate. Okay, what's the integral of 2y squared dy? Y cubed? Okay, plus the y to the third. And then what's x squared? So not 2/3, it would just be 1/3 in this case, right? There was no 2 out front. So it'd be 1/3 x cubed plus c. All right, so far so good, okay? So yep, so 2/3 y cubed, then we'll put those c's together. Okay, and then did you isolate the y too, Chanda?
Yes.
Okay, so what's our next step then to get the y, start getting the y by itself?
Multiply both sides by
3 halves, right, so we get y cubed equals, okay, so 3 halves times 1/3 is going to be 1/2.
Yes.
And again, just plus c, because the c kind of absorbs that. And then last step here, Chanda? Cube root both sides. So we get y equals the cube root of 1/2 x cubed plus c.
Like it.
And so there's the final answer. Questions on any of that? So again, and a question. You're good? So one thing I want to point out, again, we could get a slope field for this. This slope field, right, would be kind of like the generic solution to any particular, point that we use. So if we graph the slope field for this, and we pick a point on that slope field, and then, use, like we did before, we sketch the curve from that point, if we use that same point and plug it in here for the c, or plug it in here to solve for the c value, and we graph this, that graph should match our approximation when we graph the slope field here. Okay, the slope field, we use that to approximate what this graph looks like for that particular initial value. We're going to look at that some more when we come back tomorrow. Okay, homework.
No.